In the previous class, we were discussing UJT Relaxation Oscillator. Okay. As I told you, circuit diagram is very simple, similar to that of your voltage divider bias. Okay. But only difference is, so first let us draw the structure similar to voltage divider bias. Okay. So obviously, we will use UJT. Okay. Right, and I hope all of you remember that this is the symbol of UJT. Okay, so voltage divider bias arrangement, but only difference we have is we have a capacitor here. Okay, in voltage divider bias, at this place you have a resistor, but in this circuit you have a capacitor here. That is the only difference. Okay, now let us name the supply as VDB, right? Then let us name the two resistances, right? The bottom resistance R1, top resistance R2. Next, this particular, see what happens is this capacitor charges through this resistor. Okay, so the time taken for the capacitor to charge will depend on this R value, C value. Hence, they are known as timing, resistor, timing capacitor, represented by RT and CT. Okay. Next, what we will do is, see, simple. The transistor has three terminals: emitter, okay, base 1, top is base 2, right? We will simply observe the waveforms at the three terminals. So first, what happens at emitter? What happens? This is emitter terminal, okay, that is at CT, capacitor CT, which is also the emitter terminal of UJT. What happens here? Okay, so first let us discuss what happens in this particular circuit is initially, when we connect this and when we switch on, the capacitor CT will charge via RT. Okay, any resistor capacitor you connect to supply, the capacitor gradually charges. Okay, right? So first, when you switch on the supply, this capacitor CT gradually charges. When the capacitor CT gradually charges, the voltage at this point it rises. Okay, the voltage at CT, the voltage in between RT and CT, the terminal, which is the emitter terminal of UJT, the voltage at that point gradually rises as the capacitor CT charges. Now, when that voltage rises, okay, in the previous class we have discussed the characteristics of UJT. You have peak point and valley point. So when that voltage at CT, across CT, when that voltage goes above peak voltage, then UJT will turn on. When UJT is on, okay, the capacitor will start to discharge through UJT and R1. Okay, right? Next, so the capacitor will continue to discharge. When the voltage, at this node, when the voltage at this node, when it becomes less than, when it becomes less than the valley voltage, then the UJT will become off and the capacitor will start to, charge once again via RT. So initially capacitor will charge through RT, right? And then what happens when the voltage across CT becomes greater than the, when the voltage across CT becomes greater than the peak voltage of UJT, then the capacitor will discharge, right, in this path. Until which point? Until the valley point is reached. Once valley point is reached, again the capacitor will charge through RT. Okay, right? So charging, discharging of the capacitor will take place. Because of that, we have this particular waveform at CT. Capacitor is charging, discharging. Okay, charging, discharging. Charging through RT, discharging through UJT and R1. Again, charging through RT, discharging through UJT and R1. Okay. So this is what happens at this terminal, at the emitter terminal. Okay. Next, we have two output terminals. Okay. The bottom one is V01, top one is V02. Right. Now let us see what happens at V01. Now, as long as the capacitor is charging, okay, say from this point to this point, at the same instance, V01 is 0, because only after the capacitor has charged, then only UJT is becoming on, right? So initially V01 is 0. Okay, so we are drawing 0. Now at this point, when CT, voltage at CT is maximum, okay, there the UJT will turn on. So when the UJT is turning on, current will start to flow through R1. Okay, and that the switching time of the UJT is very fast. So suddenly, okay, suddenly large current will start to flow through R1. So the voltage V01 will suddenly rise to a high value. Okay. Next, but as the capacitance gradually, as the CT gradually discharges, okay, right, as time goes on, the current will reduce. Okay, see, more the capacitance, okay, when the capacitance has more charge, it can discharge more. Okay, suppose there is tank, water tank, 100 liters, right? When the tank is full, you open the tap comes with much pressure. But when the tank is empty, when you open the tank, when you open the tap, the pressure is less. Same. So as time goes on, the capacitance will start to discharge. Okay, right? So because of that, the current will gradually reduce. The current will gradually reduce, it will become 0. Until what point? Until you receive the next peak, next top peak of voltage across CT. Until that point, okay, the V01 will be low. After that, it will simply repeat itself. Okay, all right. So this is what we get at V01. Exactly opposite of that, you get at V02. V02, at V02, you simply get exactly opposite of that. Okay. Next, so here, what is happening during this? Capacitor is still charging. Okay, so UJT is, okay, off. So I will write UJT is off. Okay. Next, so what is happening when the capacitance reaches maximum voltage across it? Then UJT is turning on. So here UJT is on. Okay, right? So I will write UJT is on. Okay. Simple. As long as the output voltage is low, V01 is low, UJT is off. So UJT is off here. Okay, from here to here, UJT is off. Next, from here to here, UJT is off. Okay. Next, from here to here, the UJT is off. So only when you have this pulse, only there the UJT is on. Okay. Next, so let us, whatever we have discussed, let us write it in terms of points. So what is first? CT charges through RT. Okay. CT charges through RT. Whatever explaining for your benefit, I am writing in terms of points. Okay. So when CT charges, this voltage, okay, this is emitter terminal, right? So I am calling VE. VE will start to rise. Okay. UJT relaxation oscillator. Okay, right? And the circuit diagram is very, very simple. As I told you, similar to voltage divider bias. Of course, you have UJT in place of, okay, the transistor. But voltage divider bias circuit, in place of a resistor, you have a capacitor CT. Okay, right? So I am revising this again so that it is easy for everyone. Okay, right? So what happens here? When you connect this circuit, when you switch on, the capacitor CT charges via RT. Okay. So when the capacitor CT charges, the voltage at emitter E raises like this, reaches maximum. What is that maximum? That is the peak voltage of the UJT. At that point, UJT turns on. When UJT turns on, it starts conducting. So the capacitor will start to discharge. Okay. So when the capacitor discharges, VE reduces. Okay. And when this VE reaches the valley voltage of the UJT, again the device becomes on. Again the UJT becomes, okay, right? It, when it reaches the valley voltage of the UJT, again the UJT will now turn, okay, into the off condition. So the capacitor will charge again. Once again, I repeat, when you connect this circuit, when you switch on, the capacitor CT charges, okay, until the voltage VE becomes the, okay, it becomes the peak voltage, okay, voltage at the peak point of UJT. UJT turns on. When UJT turns on, capacitor discharges, so VE reduces. When VE becomes equal to valley voltage, then again the transistor becomes off, so the capacitor will charge via RT, right? Again, when the capacitor voltage reaches the peak voltage, peak point, the transistor again becomes on, so capacitor will discharge. The graph is like this. So what is happening here? CT charges through RT until V reaches peak point. After that, CT discharges through UJT as well as R1. Okay. So the UJT resistance is this part. Okay. It discharges to this part. So RB1 plus R1 until what point? Until valley point. Okay. Simple. So what happens when the, okay, what happens when the capacitor is charging, say the first half cycle, right? Then what happens? UJT is off. UJT is off means no current through R1. No current through R1 means V01 is current through R1 into R1. Okay, so current through R1 is 0 means R1 into current V01 is 0. That is the reason the V01 is 0, right? Next, here at this point, the transistor turns on. UJT turns on. When UJT turns on, large current will flow, large current into R1, so large voltage. That is the reason the voltage is suddenly jumping high. Okay, right? Next, now the capacitor will slowly discharge. Okay, so when it is losing charge, obviously the current reduces. When the current reduces, the voltage reduces. Okay, same cycle is repeated. So here UJT off. Only when you have the pulse, there only the UJT is on. Okay, right? Exactly opposite of this we get at V02. Right? So this is UJT relaxation oscillator. Oscillator is a circuit which generates AC signal without giving any AC input. By itself, it generates a AC signal. Okay. So next topic that we discussed in the previous class, Varactor diode. Other names of that is vary cap, because you can vary the capacitance. Okay, also known as voltage variable capacitor, right? Also tuning diode. You can control the capacitance, you can tune the capacitance based on the applied voltage. Okay, and what we have seen the general structure of a PN junction, right? What do you have in a PN junction? P region, N region, depletion region. Okay, width of the depletion region W. Now, when you increase the reverse bias, the width of the depletion region increases, right? Okay. So, when you increase the reverse bias, width of the depletion region increases. We know the formula for, okay, this particular capacitance is the what capacitance? Transition capacitance. Okay. The capacitance under reverse bias PN junction, right? It is transition capacitance. The formula we have already derived in first unit. CT is epsilon A by W. So when the reverse bias increases, okay, when the reverse bias increases, what happens? The width of the depletion region is increasing, but according to this relation, CT is inversely proportional to the width of the depletion region. So when width increases, CT reduces. So when reverse voltage is increasing, the capacitance of the diode, okay, reduces. Hence, it is useful as a voltage variable capacitor, right? So according to this, if we increase the reverse voltage, capacitance reduces. How that reduces? It reduces according to this graph. You know very well that reverse voltage, we give negative voltage. So that is the reason we are drawing this graph in the second quadrant. Okay. Applications of Varactor diode, because of its ability to, okay, control capacitance by using voltage, is useful in tuned circuits, FM modulators, automatic frequency control devices, and adjustable band pass filters. Okay, right? So all this because you can tune the capacitance based on the voltage. If you are able to tune the capacitance, you know impedance of a capacitor 1 by j omega c, okay, or 1 by j 2 pi fc. Frequency is involved, so you are able to control the frequency at which your circuit operates, right? Next, it is also useful in parametric amplifier. Okay, what do you mean by that is, if you see x again, xc, right? Xc is 1 by 2 pi fc, right? So when we are able to change capacitance, you are able to change the impedance, okay, and as a result, you are able to change the parameters of a circuit. Hence, it is useful in parameter amplifiers and also useful in television receivers. This also we have seen in the morning class. the last topic of third unit, photodiode. Remember, we are operating in reverse bias. Okay. We will take two cases. Reverse bias means, you know very well, P side negative, N side you are connecting positive of the battery, right? And resistor R to protect your photodiode. We will take two cases. Normal condition means when we don't give light. Next, when light is incident on the PN junction. So normal condition, only leakage current is flowing or reverse saturation current is flowing. When light is incident on the photodiode, okay, on the PN junction of the photodiode, as I told you, there is a window through which light can pass, and through that light is incident on the PN junction of the photodiode, right? Then what happens? The electrons, they take energy from the light, they come out of valence band, okay? They break covalent bonds and they come out. So when that happens, there is an electron in the conduction band, right? In the valence band, there is a missing electron, which is hole, okay? So as a result, electron hole pairs are generated. Electron hole pairs are generated means charge carriers, okay? You have large number of charge carriers, means current increases. Simple. You put light, the current through the device increases. You increase the intensity of the light, the current increases. So light intensity, if you increase, the current increases. The point at which you don't give light and there is leakage current, that current is called as the dark current, represented by I lambda. Okay. Next, we have seen the characteristics of the ordinary PN junction diode like this. That is, when you don't give any light, the photodiode follows the same characteristics of that of an ordinary PN junction diode. 0 lumen per meter square, no light intensity. So this first, okay, simply follows the characteristics of an ordinary PN junction diode. Now, according to this graph, when we increase the light intensity, the current increases. So, for example, if you give 10,000 lumen per meter square, then the current increases. So, the graph follows this path. Further, if you increase the light intensity, further the graph shifts downward. Okay, right? So, all this happens under reverse bias condition. If you increase the light intensity, how the graph shifts downward because the current increases, because the electron hole pairs increase, right? Okay. All this we have seen in the morning class. This was a quick revision, right? Next, we will go for applications of the photodiode. So first, it is useful in alarm systems. Okay, suppose somebody comes, suppose some thief comes, right? What you can do, you can put a light beam, and when the person crosses the light beam, right, the light is deflected, and photodiode works when light is deflected, it gives a signal, right? Based on the light intensity, the current changes. So using this signal, you can generate alarm, right? You can use that as a sensor and you can generate alarm. Next, it is also useful in counting. Suppose people are walking inside home. Each person, they are coming inside, they are obstructing the light beam. So when that light beam, when the obstructed light beam falls on the diode, the signal is received, right, at the end of the diode. That can be used for counting systems. So alarm systems, counting systems. Next, it is also useful in variable, okay, resistance devices. What do you mean by variable resistance device? Depending on the light, current is changing. For a fixed voltage, okay, for a fixed voltage, current is changing means resistance is changing. Based on the light intensity, you can actually control the resistance. Hence, it is useful in variable resistance device. Next, it is also used in light intensity measurement. Depending on the light intensity, the leakage current, okay, the reverse current changes. Using this principle, you can actually measure, right, the light intensity, or this photodiode is useful in light intensity meters. And this switching, you give light, the device starts to conduct. So it is light operated switch, and the switching happens at high speed. So it is useful in high speed logic circuits. Also, if you see fiber optic communication, what do you have at the output of what happens in a fiber optic? Okay, what happens in a fiber optic is the data is transferred in the form of light. Okay, so at the output of the fiber optic, right, the optical fiber, you can actually put a photodiode. So based on the light that falls on the photodiode, it will convert the light into electrical signal, and you can process that electronically. So it is useful in fiber optic receivers. So these are the applications of, okay, these are the applications of your photodiode. Next, let us see the equation for current in a photodiode. So to understand first, let us see the general equation of current in a ordinary PN junction diode. What is the equation of current in ordinary PN junction diode? Anybody remember? I is equal to I naught into e power V by eta Vt minus 1. So same thing is valid here. Okay, I is equals to I naught into e power V by eta Vt minus 1. Okay, but remember, we are operating the device under what bias condition? We are operating the device under reverse bias condition. Okay, operated photodiode always operated in reverse bias condition. So reverse bias condition means obviously the current will be negative. Okay, obviously the current will be negative. So I am putting a minus sign, right? And here, based on the light intensity, the current is changing. Okay, so depending on the light intensity, we have to give one more current component. Let us call it as Is. Okay, so this is the complete equation for the photodiode, complete current equation for the photodiode. Further, we can simplify this. This minus let us take it inside. So it becomes, if this minus, if we take it inside, e power V by eta Vt will be minus 1, will become 1 minus e power V by eta Vt. Okay. So simply taking this minus inside the brackets, we can write this I as Is plus I naught into 1 minus e power V by eta Vt. Okay, right? So this is the diode current equation for the photodiode. Okay, and what is eta? Eta we know very well. Okay, it is either value 1 or 2, right? So it is 1 for germanium and it is 2 for silicon. Same like an ordinary PN junction diode we have seen in first unit. Vt is volt equivalent of temperature. Okay, what I want to say is all these parameters we already know. I naught is reverse saturation current. the only new term here is IS. Okay, so what is IS here? IS is the short circuit current. Okay, IS is short circuit current proportional to the intensity of light. Okay, short circuit current proportional to light intensity, because more the intensity of light, more is IS. Okay. So with this, we complete third unit. Next, we will go for the fourth unit. Okay. Next, we'll go for unit number 4. Any doubts so far, students? Okay. So all of you should study these 3 units perfectly. Also complete assignment whenever you are coming. Shortly, I think you will be coming to college. Whenever you come to college, you have to show the 3 units assignment. Okay. The most important questions I have given as assignment. Okay. So we will start unit 4. So what is unit 4? It is analysis and design of small signal low frequency UJT amplifiers. Okay, unit 4 is analysis and design of small signal low frequency BJT amplifiers. Okay. Second unit we have seen BJT, right? So I expect all of you to study that and come. If you study, see first 3 questions in the question bank, the same repetition of what we have studied in second unit. Okay. So directly we will start with the, in this one directly we will start with the transistor hybrid model. Okay. So first, what we will do in this unit is we will analyze BJT amplifiers. Okay. We will not consider the high frequency. What happens at high frequency? We will not consider. Okay. That is the reason the title says low frequency. Then we will give small signal. Okay. We will not give large signals as input. We will consider only small signals as input. When input is small, obviously the output is also relatively small. Okay, right? Which means that we will assume the transistor parameters to be constant. Okay, that is, we will say that the transistor parameters are not changing, they are constant. Okay. So first hybrid model. Next, what we will do in this is, in this unit, we will analyze amplifiers. For example, C amplifier we have seen, right? Best biasing among all is voltage divider bias. So by default, most of the cases we will use voltage divider biasing. Okay. And directly we cannot analyze the transistor circuit. Okay. So what we will do? First, we will take AC equivalent of our circuits, and in that AC equivalent, we will replace the transistor by its hybrid model, or also known as H parameter model, which we are going to discuss now. Okay, so let us first generalize this. Any system, for example, amplifier, you have input, you have output, right? So the in between block, I will draw something like a black box. I will just draw input. Okay. Input means input voltage, input current. Output means output voltage, output current. So input I will write VI, input current II. Okay. Next, output voltage V0, output current I0. The way this model is built such that all the input current is also entering, output current is also entering the entering the transistor amplifier, right? So far any block, for example amplifier, it has input output, correct? Input we are representing input voltage, input current. Output we are representing output voltage, output current. Okay. So now total you have 4 variables. Input voltage Vi, Ii, V0, I0. Usually among these 4 variables, 2 variables are considered as independent variables and remaining 2 are expressed in terms of these independent variables. Okay. Depending on what you choose as the independent variables, you have different parameters. Okay. So here, if you see transistor, we know very well that transistor is current controlled device. Means the output current depends on input current. So let us write like this. The output current I0 depends on input current. Some constant I will take multiplied by input current. Okay. Not only the output current is depending on input current, output current also depends on output voltage, isn't it? So I will take one more parameter, okay, and I will represent output voltage. See, output current is a function of input current because BJT is a current control device, and the output current is a function of output voltage, isn't it? More the output voltage, more the output current. Okay, common sense. So based on this statement we are representing mathematically like this, right? So here II, V0 we have to choose as independent variables. So what is the other variable? Other variable is Vi. Okay, I0 is over, II is over, V0 is over. So Vi also we can now represent in terms of II and V0. So Vi let us represent in terms of II and V0. All the 4 places the proportionality constant, okay, I have taken as H, right? But we have to take different proportionality constant. So what I will do is I will call it H11, H12, H21, H22. Okay, 1 1 1 2 2 1 2 2, something like matrix. Okay, mathematics matrix. Next, here let us try to define what are these 4 parameters. Now you have 4 parameters: H11, H12, H21, H22. These are called as hybrid parameters because, okay, they are not all having the same unit, which we will now see shortly. So how you can define H11? Suppose if we make V0 0, suppose V0 is 0, then H11 is simply Vi by II. So H11 is Vi by II when V0 is 0. Okay. H11 is Vi by II when V0 is 0. Likewise, next let us see H12. How can you get H12? Suppose II is 0. Suppose II is 0. So first term in first equation is missing. II is 0. Then H12 is Vi by V0. Suppose II is 0, then Vi is H12 into V0. Cross multiply this V0 to the other side. So H12 is Vi by V0 when II is 0. Okay. Vi by V naught when II, okay, Vi by V naught when II is 0. Next, what will H21 be? H21 will be, okay, similarly, I naught by II when V naught is 0, okay. H21 is I naught by II when V naught is 0. Last H22, anybody will answer what will H22 be from this equation? Students, what will H22 be? I naught by V naught when II is 0, okay. I naught by V naught when II is 0, okay. Okay. So, these are the 4 H parameters or hybrid parameters, right? Now, let us see what we can name them. Let us now try to give names to these 4 parameters. See here, H11 is input voltage by input current. Voltage by current is resistance. Input voltage by input current will be input resistance, right? So, it is input resistance when V naught is 0, correct? How to make voltage 0? Short circuit. So, input resistance when output is short circuited, okay? Input resistance with output short circuited. Next, H12. What is H12? It is input voltage by output voltage, okay, right? It is the ratio of input voltage by output voltage. You know, voltage gain is output voltage by input voltage, right? So, this is like reverse voltage gain. V naught by Vi is voltage gain. Vi by V naught, you can call it as reverse voltage gain. So, if we can call this as reverse voltage gain. But the condition is II is 0. How to make current 0? Open circuit. Okay. So, with I means input. I, the subscript I indicates input. Okay. So, with input open circuited. Similarly, okay. Similarly, H21 will be I naught, H21 is I naught by II. Output current by input current. It is simply current gain, but previous case we called reverse voltage gain. So, we will call this as forward current gain. Okay. We will call this as forward current gain. Okay. Forward current gain with V naught 0. V naught is output voltage. Okay. Output voltage 0. Output voltage 0 means output short circuit. Output with output short circuited. Next, H22 I naught by V naught. Voltage by current is resistance. Current by voltage. What is that? Anybody? Current by voltage is admittance. Okay. So it is output admittance with II0. II0 means input open circuited. Okay. With input open circuited. Right. So these are the names of the 4 H parameters.